Hello, I'm Dmitrii, and this is the video abstract to my contribution to the Journal of Number Theory titled On Sets with Small Additive Doubling Inside Product Sets. We start with some background material from additive combinatorics. The product set of a set B is defined as a set of full pairwise products B times B prime, where B and B prime are two elements from B. And likewise, the sum set is defined as a set of full pairwise sums B plus B prime, where B and B prime are two elements from B. The very basic property is the additive doubling, defined simply as the quotient of two sizes of the sum set and the original set B. So if the additive doubling is small, one should expect that B is somehow additively structured, and indeed this is a deep theorem of Freiman. However, often it is better to consider another property, which is the additive energy of the set B. It is defined as the number of solutions to the equation b1 plus b2 is equal to b3 plus b4, where b1, b2, b3, and b4 are of course elements of B. Let's look at a few examples why the additive energy is better than the additive doubling. Well, the very basic example is when b is just the set of integers from 1 to n. And in that case, we can explicitly calculate the additive doubling, which is bounded by 2. And of course, B is additively structured, because this is simply an arithmetic progression. Likewise, the additive energy is large, because it is of size n squared, n cubed, which is the size of the original set B cubed. And obviously, this is the maximal additive energy a set can have. However, if we take our set B as the union of the integers from 1 to n and the powers of 2, then it is easy to say that the additive doubling is large. However, the additive energy is again almost as maximal as it could be, because B still contains the interval from 1 to n. And that's why the additive energy is of order n cubed, and that's why it is of order of b to the power of 3. Now we come to the main result of our paper. First, consider the product set of the integers from 1 to n and itself. The very obvious observation is that it is contained in the interval from 1 to n squared. However, it is not even dense, as follows from the classical result of R', saying that the size of this product set is actually little o of n to the power 2. Using Cauchy-Schwarz, it is easy to reformulate this result of R' in terms of the additive energy of the product set, which in this case is little o of n to the power 6, as n goes to infinity. So the main result of our paper is a generalization of this classical result of R', which is called the multiplication table theorem, for any integer set B, modulo some growth condition. Namely, we prove that under a certain growth condition for any integer set B holds the estimate for the additive energy, namely that the additive energy of the product set B times B is asymptotically little o of b to the power 6, as the size b goes to infinity. We refer the interested reader to the paper for details, and I thank you for your attention. Bye bye.